In any large-scale IT research and development campus today, continuous integration and deployment pipelines operate around the clock. Thousands of code commits are integrated, built, and pushed to production environments every single day. Then, a front-end developer makes a microscopic adjustment. They update a button's ID string or slightly alter the document object model to accommodate a new layout. That single trivial adjustment triggers a chain reaction. Hundreds of automated test scripts suddenly throw red failure alerts, collapsing the entire testing suite. Development grinds to a halt while engineers manually investigate these false alarms. This specific type of maintenance overhead drains a minimum of 2.5% of total developer productivity, translating directly into severe financial losses for the organization. Standard production code is subjected to strict architectural design, peer reviews, and rigorous configuration management. Test automation scripts, conversely, are frequently written on the fly, creating monolithic, brittle codebases that shatter at the first sign of UI variation. Organizations fail here because they treat test automation as a supplementary macro. They view it as a simple utility meant to blindly record and click through screens, rather than a demanding engineering discipline. A true test automation solution requires its own distinct architecture. It needs dedicated documentation, version control, component testing, and quality verification to ensure the testing code itself is structurally sound. If the testing code is unreliable, the quality metrics it generates are meaningless. Extracting a positive return on investment is impossible unless the automation suite is engineered with the exact same rigor as the commercial software it aims to test. The first step to stabilizing an automation suite has nothing to do with writing test scripts. The focus must start on the architecture of the actual software being tested, the system under test, or SUT. Software engineers rarely build systems with automated testing in mind. When a system lacks intrinsic testability, automation engineers face structural barriers that guarantee their scripts will fail. First is observability. The system under test turns transparent, exposing internal API responses and logs directly to the automation framework. Second is controllability. An external dial locks off incoming network connections and forces specific database states, removing external latency variables the suite cannot control. Teams achieve this control in microservice architectures through service virtualization and mocking. By replacing unpredictable external APIs with controlled, simulated responses, the testing environment remains completely isolated. Without deep observability and precise controllability to isolate the system, hidden state changes and network lag mathematically guarantee non-deterministic, flaky test failures. How engineers write test scripts dictates the long-term survival of the automation project. Early approaches relied on record-and-playback methods, which yielded fast initial scripts, but forced total code abandonment the moment a single UI element moved. The industry later shifted toward behavior-driven development frameworks. These utilize natural language formats, like Gherkin syntax, allowing non-technical stakeholders to read the test scenarios as simple English sentences. This matrix reveals the hidden cost of natural language frameworks. Beneath simple sentences lies a massive translation layer of glue code that inflates, draining the engineering budget. Conversely, keyword-driven methods demand high initial skill, but yield a significantly higher return on investment over the software's lifespan. Adopting frameworks specifically because they make writing tests easier for non-programmers, without enforcing strict underlying architectural discipline, guarantees skyrocketing maintenance costs. To contain those maintenance costs at an enterprise scale, the International Software Testing Qualifications Board defines a structural blueprint, the generic test automation architecture. This blueprint relies on extreme architectural isolation. It physically breaks the automation suite into 4 distinct functional layers, ensuring that changes in one area do not corrupt the others. This stack visualizes the hierarchy. The top block, the test generation layer, houses abstract models and test cases. Below it locks the test definition layer, containing the business logic and precise scripts. Finally, the test execution layer runs engines, executes commands, and manages reporting mechanisms. These 3 upper layers hold the core logic, but they are entirely defenseless against structural changes to the physical application. That defense relies entirely on the final, foundational layer of the stack. The structure physically separates what the business logic is trying to achieve from the mechanical reality of how the system executes it. The test adaptation layer acts as a firewall above the system under test. Implementing the adapter pattern, a high-level command flows down into the adapter and is translated into specific technical protocols, finding DOM element IDs, executing GUI clicks, and posting API requests. When the target software's UI or API endpoints inevitably change, the business logic scripts in the upper layers remain completely untouched. Engineers only need to update the isolated adapter code. Architectural isolation protects the code, but execution isolation protects the results. This introduces the requirement for a strict test fixture, defining the baseline state of the system before any script runs. True test atomicity requires ruthless housekeeping. If a script writes a record to a database, that transaction must be rolled back. Memory must be wiped completely clean after every single session, so the next script starts from an identical baseline. Without aggressive post-test teardowns, independent tests become secretly coupled by leftover state data. The leftover debris from one test corrupts the environment, unleashing a chain reaction of false alarms across the pipeline. Deploying this multi-layered framework across an entire organization using a Big Bang approach carries immense risk. Teams must execute a strictly controlled pilot project. This limits the blast radius while proving the architecture's viability on a narrow subset of the software. The pilot must validate non-technical constraints. Management must assess if the current team possesses the engineering skills to maintain the adapter layer, verify that software licensing costs will scale efficiently, and prove the framework can adapt if the company migrates to microservices. Once deployed, the automation code must be managed as a living organism. Production code and the scripts built to test it, collectively known as Testware, evolve together. Software teams often fall into a hoarding mentality, keeping thousands of old scripts active. When software features are retired or their core functionality is redesigned, the accompanying testware instantly degrades into toxic technical debt. Engineers must enforce a rule of ruthless deletion. If an aging test consistently generates false alarms, or if the hours spent maintaining it exceed its business value, it must be either heavily refactored or permanently deleted. High ROI test automation is never achieved simply by writing more test scripts. It is engineered entirely through a resilient, decoupled architecture built to absorb inevitable change.